There is a piece of rock beneath the Australian outback that is 3 billion years old. Not 300 years, not 3,000, 3 billion. When this rock solidified, there was no complex life on Earth. No fish, no trees, no dinosaurs. The atmosphere was toxic. The oceans were shallow and warm and full of single-celled organisms that had not yet figured out how to become anything else. And this rock, this enormous, cold, rigid slab of ancient continental crust, sat beneath all of it, through every mass extinction, through every ice age, through the entire history of complex life on this planet, from the first worm to the first human to this exact moment. It did not move. For 3 billion years, this rock did not move, until April 4th, 2026. A magnitude 5.5 earthquake tore through the Australian outback 77 kilometres from Uluru. Guests in a nearby hotel were jolted awake at night. Fixtures swung. Objects fell. People reached for their phones in the dark, looking for an explanation. The explanation they found was technically accurate, but scientifically incomplete. Because here is what the news reports did not tell you. This region of Australia, the Musgrave Block, one of the oldest and most mechanically stable pieces of continental crust on the surface of this planet, averages less than one significant earthquake per decade. Not per year, per decade. And this earthquake arrived 36 hours after the strongest geomagnetic storm of 2026. It also arrived as the 5th major earthquake in 14 days. The previous 4 struck along the Ring of Fire, exactly where earthquakes are supposed to happen. Active subduction zones, known fault systems, plates grinding against plates in the way they have for hundreds of millions of years. But this one was different. This one was 4,000 kilometers from the nearest plate boundary. Now, before we go any further, I want to be clear about something. This documentary is not going to tell you that solar storms cause earthquakes. That is not what the science says. What the science says is more interesting and more unsettling than that simple claim. What the science says is, we don't fully know, and the reason we don't fully know is that the Earth is not a closed system sitting quietly in empty space. It is a layered, electrically active, magnetically sensitive planet embedded inside a star's constant outpouring of energy. And the boundary between what happens up there and what happens down here is less clean than most models assume. That boundary is what this documentary is about. We are going to go deep. We are going to start with the rock itself, what it means for crust to be 3 billion years old, why that matters, and why geophysicists who specialize in crustal mechanics looked at the April 4th event with something between fascination and genuine discomfort. Then we are going to follow the full 14-day sequence, earthquake by earthquake, and show you the solar storm timeline running alongside it. Then we are going to go further than any breaking news report did, into the physics of how a magnetic storm interacts with the solid Earth, into the open scientific debate about whether these systems are truly separate, into what this sequence reveals about the limits of our current models. And we are going to end somewhere honest, not with false certainty in either direction, but with a precise understanding of what this event proved, what it didn't prove, and what it forced scientists to look at more carefully. Stay with this, because the earthquake near Uluru is not just a seismic event, it is a classification problem. And in science, classification problems are not dead ends, they are doorways. To understand why April 4th matters, you have to understand something that human beings are genuinely bad at understanding. Not because it is intellectually difficult, but because it requires the brain to hold a scale of time that it was never evolutionarily designed to process. We are wired to think in seasons, in generations, in centuries, at the most ambitious stretch of our intuitive temporal imagination. What geology asks of us is something categorically different. It asks us to genuinely feel the weight of billions of years. Not just to say the number, but to let it land. The tool geologists use for this is called deep time. The term was popularized by the writer John McPhee in 1981, but the concept itself was first articulated by the Scottish geologist James Hutton in the late 18th century, when he stood at a rocky outcrop on the Scottish coast called Siccar Point and realized he was looking at a boundary between two rock formations that represented an almost incomprehensible gap in the geological record. Below the boundary, ancient rocks tilted nearly vertical, remnants of a mountain range that had risen, been eroded flat of an end. It was a profound and slightly vertiginous moment in the history of human thought. The Earth was not thousands of years old, as the prevailing intellectual framework assumed. It was unimaginably, incomprehensibly old, and the rocks recorded that age in layers, in unconformities, in the slow, patient language of stone. We now know that the Earth is approximately 4.54 billion years old. That number is established through radiometric dating, the measurement of the decay rates of radioactive isotopes in rocks and minerals, and it is one of the most precisely determined fundamental constants in all of natural science. To put 4.54 billion years in a frame that the brain can hold, consider this. If the entire history of Earth were compressed into a single 24-hour day, with Earth's formation at midnight and the present moment at the following midnight, then the first simple single-celled life would appear around 4 in the morning. The first complex multicellular animals, the Cambrian explosion of animal body plans, would not appear until around 9 in the evening. The dinosaurs would not arrive until about 11 p.m. They would go extinct at 11:39. Modern humans, our entire species, would appear in the last 2 seconds before midnight. And the entire span of recorded human civilization, from the first writing systems to the present day, would occupy roughly the last 1/10 of a second. Everything we know, every book ever written, every city ever built, every war ever fought, 1/10 of a second on a 24-hour clock. The rock beneath the Australian outback formed during the equivalent of mid-morning on that clock, around 9 to 10 a.m. in the deep time day. The surrounding components of the Australian shield carry ages approaching 3 to 4 billion years, placing their formation even earlier, in the first hours of Earth's geological morning. To understand what that means physically, you have to understand what was happening to the Earth during those early billions of years that it was not doing later. The early Earth was a fundamentally different planet. Its interior was hotter, the heat of formation had not yet dissipated, and the decay of short-lived radioactive isotopes was generating additional internal heat at rates far higher than today. The mantle was more vigorously convecting, turning over in great slow currents of solid rock behaving plastically under extreme pressure. The surface was being continuously reshaped by impacts, by volcanism on a scale that dwarfs anything in the modern geological record, and by the gradual assembly of the first stable continental crust. The process by which continental crust forms and stabilizes is complex, but the essential physics is this. Mantle convection brings hot material upward. That material melts partially as it rises, and the pressure decreases. The melt, magma, is less dense than the surrounding mantle rock, so it rises further, intruding into and erupting through the overlying crust. As it cools, it crystallizes into igneous rock. Over time, repeated episodes of this process build up thick accumulations of relatively low-density rock that float on the denser mantle beneath, the same way ice floats on water, because ice is less dense than liquid water. Continental crust is, in essence, the foam that formed on the surface of a vigorously boiling planet and gradually cooled, thickened, and stabilized over billions of years. The oldest stable portions of continental crust, the cratons, are the pieces of that ancient foam that survived. That did not get recycled back into the mantle through subduction. That did not get obliterated by later collisions. That found a kind of mechanical equilibrium, thickening and cooling until they became so dense and rigid and cold that the mantle convection currents could no longer efficiently drag them downward. A craton is, in the most literal physical sense, the part of the original Earth that refused to be destroyed. The Pilbara Craton in northwestern Australia contains some of the oldest rocks on Earth, ancient gneisses and granites with ages approaching 3.6 to 3.8 billion years, preserving a mineral and chemical record of conditions on the early Earth's surface that exists nowhere else. The Yilgarn Craton to the south is similarly ancient. And the region that concerns us today, the Central Australian geological province that includes the Musgrave Block, formed somewhat later, approximately 1 to 1.2 billion years ago, during a period of continental collision and mountain building known as the Musgrave orogeny. By geological standards, this makes it a relative newcomer. By any other standard, it is incomprehensibly old. What happens to rock over a billion years of sitting still? A great deal, and almost none of it is visible at the surface. The most important thing that happens is cooling. In the first hundreds of millions of years after a piece of continental crust stabilizes, it is still relatively warm. Its lower portions are hot enough to behave plastically under stress, deforming slowly rather than fracturing. Over geological time, as the internal heat dissipates and the radioactive isotopes that generate heat through their decay become depleted, the lithosphere cools from the bottom up. As it cools, it thickens. The boundary between the rigid lithosphere above and the convecting mantle below, called the lithosphere-asthenosphere boundary, deepens progressively. Old cratonic lithosphere is enormously thick by the standards of younger crust, where oceanic crust at mid-ocean ridges is only 7 to 10 kilometers thick, and where young continental crust in active tectonic zones might be 30 to 40 kilometers thick. Ancient cratonic lithosphere can extend to depths of 200 to 300 kilometers or more. It is not just thick in the shallow sense. It has a deep keel, a massive root of cold, rigid, chemically depleted mantle rock that anchors it in place and makes it extraordinarily resistant to the forces that tear apart and reconfigure younger, thinner, weaker lithosphere. This is the physical foundation of cratonic stability. It is not simply that the rock at the surface is old. It is that the entire lithospheric column beneath it, from the surface to depths of hundreds of kilometers, has been cold, rigid, and mechanically strong for so long that it has become one of the most stable and immovable structures in the Earth system. The Musgrave Block sits within this cratonic framework, but with a specific geological history that distinguishes it from the simple picture of ancient undisturbed crust. Approximately 550 to 520 million years ago, still ancient by human standards, but geologically recent compared to the age of the underlying Archean basement, the Musgrave region experienced a significant tectonic event. The collision of the North and South Australian cratons produced a zone of intense deformation, metamorphism, and igneous activity that reworked the existing crust and created the complex structural fabric that defines the Musgrave Block today. This event, the Petermann orogeny, produced shear zones, thrust faults, and deep crustal discontinuities that are preserved in the rock to this day, even though the mountains that once rose above them have long since been eroded to the flat, ancient landscape of the modern outback. These ancient structural features are not merely geological curiosities. They are the inherited architecture that controls how the modern crust responds to modern stresses. When the Musgrave Block experiences a modern earthquake, it almost certainly does so by reactivating one of these ancient structures, exploiting a pre-existing weakness in the rock fabric rather than creating a new fracture through intact material. The fault that moved on April 4th, 2026 was almost certainly ancient. Its modern rupture was the latest episode in a history of deformation, stretching back hundreds of millions of years. Above all of this geological complexity sits the landscape that most people associate with Central Australia: the Red Desert, the spinifex grass and the mulga scrub and the enormous flat horizons, the iron-rich red soil that gives the outback its characteristic colour, the result of hundreds of millions of years of chemical weathering in a hot, dry, oxidizing environment that has slowly converted iron-bearing minerals in the surface, rock, into iron oxide, the same compound that makes rust red. And rising from this red landscape, Uluru, the enormous sandstone monolith that has become one of the most iconic geological features on Earth. Uluru is not a remnant of some ancient mountain. It is a single mass of arcosic sandstone, a sedimentary rock formed from the erosion and deposition of older igneous and metamorphic rocks that was deposited approximately 550 million years ago, tilted nearly vertical by the same tectonic forces that drove the Petermann orogeny, and then exposed by hundreds of millions of years of differential erosion that stripped away the surrounding softer rock while the harder sandstone of Uluru remained. What you see rising above the desert floor is not the top of Uluru, it is its edge. The bulk of the formation extends downward into the earth, with estimates suggesting the base of the sandstone mass lies several kilometers below the surface. It is, in a very literal sense, the tip of an enormous buried geological structure, and it sits 77 kilometers from where the Earth moved on April 4th. The contrast between the apparent stillness of this landscape and the violence of what occurred beneath it on April 4th is the central tension of this story. The outback looks like a place where nothing changes, where geological time has slowed to imperceptibility, where the red rock and the flat horizons and the ancient silence suggest a world that has settled permanently into its final form. That appearance is an illusion. Beneath the stillness, the Earth is never truly at rest. Before we can appreciate why the April 4th event is unusual, we need to understand what an earthquake actually is at the most fundamental physical level. Not in the simplified sense of plates moving and the ground shaking. That is accurate as far as it goes, but it leaves out almost everything that matters for understanding why some earthquakes happen where they do, why some faults fail and others don't, and why the timing of individual ruptures is so difficult to predict, even when we know a fault is loaded and capable of producing a large event. An earthquake is the sudden release of elastic strain energy stored in the Earth's crust. To understand what that means, start with the concept of elastic deformation. When you stretch a rubber band, you are elastically deforming it. The material is being strained away from its natural shape, and it stores the energy of that deformation as elastic potential energy. Release the rubber band, and that energy is converted back into kinetic energy as the material snaps back to its original shape. Rocks behave the same way, with one critical difference. Rocks are brittle. They can store elastic energy through deformation up to a point, and that point is their failure threshold. Beyond that threshold, instead of continuing to deform elastically, they fracture. And when they fracture, when the accumulated elastic strain energy is released all at once, that energy propagates outward as seismic waves. Waves that travel through the Earth at kilometers per second, shaking everything they pass through. That is an earthquake. The process of strain accumulation in the crust is driven by the motion of tectonic plates. The Earth's outer shell, the lithosphere, is divided into approximately 15 major plates and a larger number of minor ones, all moving relative to each other at rates of centimeters per year, driven by the convection of the underlying mantle. Where plates collide, one is forced beneath the other in a subduction zone, or they crumple upward into mountain ranges. Where plates pull apart, new oceanic crust is created at mid-ocean ridges. Where plates slide past each other horizontally, transform faults develop. In all of these settings, the relative motion between adjacent pieces of lithosphere creates shear stress, a force trying to make one block of rock slide past another. Most of the time, that sliding does not happen smoothly and continuously. It happens in sudden jerks, separated by long periods of apparent stillness. This is because the surfaces of faults are not frictionless. They are rough, irregular, often cemented together by mineral growth during the periods between earthquakes. The stress builds continuously as the plates move, but the fault resists sliding until the stress exceeds the frictional strength of the fault surface. Then, in a fraction of a second, meters or even tens of meters of slip occur along the fault, releasing decades or centuries of accumulated strain. That sudden slip is the earthquake. The magnitude of an earthquake is a measure of the total energy released in that slip. Specifically, it is related to the product of the area of the fault that ruptured and the average amount of slip that occurred across that area. A magnitude 5 earthquake typically involves rupture of a fault area of a few square kilometers with a few centimeters of average slip. A magnitude 7 earthquake involves a fault area of hundreds to thousands of square kilometers with meters of average slip. A magnitude 9 earthquake, the largest category of events associated with the largest subduction zones, involves rupture of fault areas tens of thousands of square kilometers in extent with tens of meters of slip. The energy scales are enormous. A magnitude 9 earthquake releases approximately 1,000 times more energy than a magnitude 7, and approximately 1 million times more energy than a magnitude 5. The logarithmic magnitude scale compresses what is actually a staggeringly wide range of energy release into a deceptively small numerical range. Seismologists classify earthquakes in several ways that are important for understanding the April sequence. The most fundamental classification is between interplate and intraplate earthquakes. Interplate earthquakes occur at or near the boundaries between tectonic plates, at subduction zones, transform faults, and spreading centers. These are the events that dominate the global seismic catalogue. Approximately 90% of all earthquake energy released globally is released at plate boundaries. The ring of fire, the chain of subduction zones, and transform faults encircling the Pacific Basin accounts for the majority of the world's largest and most frequent earthquakes. The mechanisms driving these events are well understood. Stress accumulates through plate motion, reaches a threshold, and is released in ruptures whose locations, sizes, and approximate recurrence intervals can be estimated with reasonable confidence from the geological and historical record. Intraplate earthquakes are categorically different. They occur within the interior of tectonic plates, far from active plate boundaries, in regions where the driving mechanism for stress accumulation is not the direct relative motion of adjacent plates, but rather the more diffuse and poorly constrained transmission of far-field tectonic stresses through the rigid plate interior. These events account for only a small fraction of global seismic energy release, but they are disproportionately important from a hazard perspective because they occur in regions where the population is not accustomed to earthquake risk, where building codes may not be designed for seismic loading, and where the infrastructure for seismic monitoring is often less dense than in active tectonic zones. The 1811 to 1812 New Madrid earthquakes in the central United States, a series of magnitude 7 to 8 events in the middle of the North American continent. It is tectonically active enough to produce significant earthquakes, but infrequent enough in its seismicity that each major event attracts significant scientific attention. The Australian plate as a whole is moving northward at approximately 6 to 7 centimeters per year, one of the fastest rates of motion of any continental plate. This rapid northward motion is driving ongoing collisions with the Eurasian plate at the Himalayan front and with the Pacific and Philippine plates along the northern margin of the Australian plate. These collisions generate compressional stresses that are transmitted back into the Australian continent, loading fault systems in the plate interior with a slow but continuous input of tectonic energy. The Australian continent is also notable for the high horizontal compressive stress state of its crust. Measurements from borehole breakouts and earthquake focal mechanisms consistently indicate that the crust is under significant horizontal compression in most regions. This high background stress state means that fault systems in the Australian interior are not stress-free. They are loaded, albeit at a rate much slower than the continuously driven fault systems of the Ring of Fire. The question is not whether they will ever rupture, it is when, and whether that timing can be influenced by anything other than the slow accumulation of tectonic stress. There is one more concept from fault mechanics that we need to establish before we examine the April sequence in detail. It is the concept of critical stress state. In any fault system, there is a range of stress conditions from far below failure, where the fault is stable and no reasonable perturbation could trigger rupture, to critically stressed, where the fault is so close to its failure threshold that even a tiny additional increment of stress could initiate slip. The distribution of faults across this spectrum in any given region is not uniform. Some faults are far from failure, some are moderately loaded, and some, particularly those that have not ruptured in a long time and have been accumulating stress for centuries or millennia, may be very close to failure, sitting near the top of their loading cycle, requiring only a small final push to cross the threshold. This concept of critical stress state is the key to understanding why small external perturbations, tidal forces, atmospheric pressure changes, and potentially electromagnetic effects can sometimes appear to trigger earthquakes, while at other times having no detectable effect. A small perturbation cannot create an earthquake in a fault that is far from failure. But in a fault that is already critically stressed, the same small perturbation might be the precise increment that tips the system over the edge. The earthquake was going to happen anyway. The small perturbation only determined the exact moment of its occurrence. With this framework in place, we can now look at the 14-day sequence with the analytical tools we need to evaluate what happened and why it matters. Let's build the timeline with the depth it deserves. Because each of these 5 earthquakes has a geological identity, a specific tectonic setting, a specific stress history, a specific reason why it happened where it did. And understanding those identities individually is what makes their collective behavior in this compressed 14-day window so striking. We begin at the Tonga-Kermadec Trench. If you were designing a place on Earth specifically for the purpose of generating large earthquakes, you would design something very close to the Tonga-Kermadec system. It is a subduction zone in the southwestern Pacific, where the Pacific Plate, the largest tectonic plate on Earth, covering approximately 1/3 of the planet's surface, is diving beneath the Indo-Australian Plate at a convergence rate of approximately 15 to 24 centimeters per year. This is extraordinarily fast by plate tectonic standards. Most subduction zones converge at 5 to 10 centimeters per year. The Tonga-Kermadec system is converging at roughly twice that rate in some segments, which means stress is accumulating at roughly twice the rate, which means the recurrence interval for large earthquakes is shorter and the seismicity rate is higher. The trench itself is one of the deepest in the world. The Tonga Trench reaches a depth of approximately 10.8 kilometers, making it the second deepest oceanic trench on Earth after the Mariana Trench. The subducting Pacific Plate in this region is old, approximately 80 to 100 million years old in the Tonga sector, which means it is cold, dense, and negatively buoyant, actively sinking under its own weight, in addition to being dragged down by the motion of the broader Pacific Plate. This slab pull dynamic makes the Tonga-Kermadec system one of the most tectonically vigorous on Earth. On March 24, 2026, a section of the subduction interface in this system ruptured in a magnitude 7.5 earthquake. The rupture involved sudden slip along a fault plane that likely extended for 100 to 200 kilometers along the subduction interface, with average displacements of several meters occurring in a matter of seconds. The energy release was enormous, equivalent to many thousands of nuclear weapons detonating simultaneously, and it propagated outward from the rupture zone as seismic waves that were recorded on instruments around the world within minutes. Tsunami monitoring systems activated immediately. The waves generated were real, but limited in destructive potential given the deep water and relatively distant populated coastlines. What matters for our purposes is what happened in the stress field surrounding the rupture zone after the earthquake. When a large earthquake occurs, it does not simply release stress from the patch of fault that slipped. It redistributes stress across the surrounding fault network. The regions of the fault that are immediately adjacent to the rupture zone experience what is called static stress transfer, a permanent change in the stress state resulting from the elastic rebound of the surrounding crust after the slip. Some areas experience increased stress, moving fault segments closer to failure. Others experience decreased stress, moving segments further from failure. This pattern of stress increase and decrease, called a Coulomb stress change map, provides the primary physical framework seismologists use to assess the likelihood of aftershocks and secondary earthquakes following a major event. In addition to static stress transfer, the seismic waves themselves, which are dynamic stress perturbations propagating outward from the rupture, can trigger earthquakes at distances far beyond the static stress change zone in a process called dynamic triggering. Dynamic triggering has been documented at distances of thousands of kilometers from large earthquakes, particularly in geothermal and volcanic regions where fault systems are already critically stressed and sensitive to small perturbations. 2 days after Tonga, on March 26th, a magnitude 6.5 earthquake struck offshore Japan. Japan's tectonic setting is almost as extreme as Tonga's. The Japanese archipelago sits at the intersection of four tectonic plates: the Pacific, Philippine, Eurasian, and North American plates, and is one of the most seismically active regions on Earth. The offshore earthquake on March 26th occurred along one of the many fault systems associated with the subduction of the Pacific Plate beneath northeastern Japan, the same subduction system that produced the catastrophic magnitude 9.0 Tohoku earthquake in 2011. The 2011 earthquake dramatically reorganized the stress field across northeastern Japan, loading some fault segments and unloading others, and the seismic system in this region has been adjusting to that enormous stress perturbation ever since. A magnitude 6.5 in this context is significant, but not unexpected in isolation. The question is whether its timing, 2 days after Tonga, within the same elevated geomagnetic window, reflects a connection or a coincidence. 4 days later, on March 30th, a magnitude 7.3 earthquake struck Vanuatu. The Vanuatu archipelago sits in one of the most tectonically complex regions of the southwestern Pacific, a zone where the Australian plate is colliding with and subducting beneath the Pacific plate along the New Hebrides Trench, while simultaneously a back arc spreading system is opening behind the volcanic arc. The result is a region of intense, multi-directional tectonic stress, where large earthquakes are among the most frequent per unit area of any place on Earth. Vanuatu has experienced numerous magnitude 7 and above events throughout the instrumental record, and a magnitude 7.3 in this region requires no extraordinary explanation in isolation. But on March 30th, it is the third major rupture in 6 days, and the geomagnetic environment that has been elevated since before the Tonga event has not recovered. The solar wind driving is continuing. The magnetosphere is not at rest. On April 1st, the sequence reached the Maluku Sea between Sulawesi and Halmahera in Indonesia with a magnitude 7.4 earthquake. The Maluku Sea region deserves special attention because it is one of the most structurally complex seismic environments on the planet, a place where the standard two-plate subduction model completely breaks down and is replaced by something far more intricate. In this region, multiple small plates and microplates are actively colliding, rotating, and being consumed simultaneously. The Maluku Sea collision zone, where two separate volcanic arcs are being thrust against each other simultaneously from opposite directions, produces a three-dimensional stress field of extraordinary complexity. Earthquakes here do not fit neatly into the simple framework of one plate subducting beneath another. They reflect a chaotic, rapidly evolving tectonic environment where stress accumulates and releases in multiple directions simultaneously. A magnitude 7.4 in the Maluku Sea is consistent with the region's seismic character, but its timing, the fourth major earthquake in 9 days, all occurring during a period of sustained elevated geomagnetic activity, has pushed the sequence into territory where a purely coincidental interpretation is becoming increasingly difficult to maintain with complete comfort. Then, April 4th. The event that changes everything about how this sequence is categorized. A magnitude 5.5 earthquake is recorded near Uluru in central Australia. Let's be precise about why this is different. The previous 4 earthquakes all occurred within the broad deformation belt of the Western Pacific, a connected system of subduction zones, back-arc basins, and transform faults that collectively accommodate the convergence between the Pacific Plate and its neighbours. Stress transfer between systems within this belt is physically plausible through both static and dynamic mechanisms. The belt is active, continuously stressed, and contains numerous fault systems that are probably near failure at any given time. The timing may be unusual, but the location of each of the first four events is entirely consistent with the known global distribution of seismic risk. The Musgrave Block event breaks every one of those constraints simultaneously. It is geographically isolated from the Western Pacific deformation belt by thousands of kilometers of stable continental interior. It is geologically disconnected from the active subduction systems of the Ring of Fire. There is no plausible static stress transfer pathway that connects a magnitude 7.5 at the Tonga-Kermadec Trench to a fault in the Central Australian craton. Dynamic triggering from seismic waves is theoretically possible at this distance, but the amplitude of seismic waves at 4,000 kilometers from a magnitude 7.5 source is small, and the Australian craton, with its thick, rigid lithosphere, is not the kind of environment where dynamic triggering is typically efficient, and yet it happened. On April 4th, 36 hours after the strongest geomagnetic storm of the year, in a region of 3-billion-year-old rock that was not supposed to move on human timescales. Now let's overlay the space weather timeline precisely. In the week before March 24th, solar wind monitoring at the L1 Lagrange point, the gravitational balance point between Earth and the Sun, where the NOAA Deep Space Climate Observatory maintains a constant vigil, was recording elevated solar wind speeds and densities associated with the passage of a high-speed stream from a coronal hole on the Sun's surface. Coronal holes are regions of the Sun's corona where the magnetic field opens outward into interplanetary space rather than looping back to the surface, allowing solar wind to flow outward more freely and at higher speeds than from the surrounding corona. High-speed streams from coronal holes are one of the two primary drivers of geomagnetic activity at Earth, the other being coronal mass ejections. The Geomagnetic KP index, a global measure of geomagnetic disturbance derived from averaging measurements from magnetometer stations around the world, was elevated in the days before the Tonga earthquake. By the time of the March 26th Japan event, the geomagnetic environment remained disturbed. By March 30th, a new disturbance interval was beginning, and by April 3rd, the strongest event in the sequence arrived. A G3 class geomagnetic storm peaking at a KP index of 6.67. To put that in context, the KP scale runs from 0, completely quiet, to 9, extreme storm. A KP of 5 is classified as a minor G1 storm. A KP of 6 to 7 is a strong G3 storm. Above 7 is a severe G4. Above 8 is an extreme G5, the category that produced the 1989 Quebec blackout and the 2003 Halloween storms that damaged transformers across Europe and South Africa. A KP of 6.67 is solidly in G3 territory, strong enough to affect satellite operations, disturb HF radio communications globally, drive auroras to mid-latitudes, and, critically, induce measurable electrical currents in conductive structures at Earth's surface, including the crust. 36 hours after that KP peak, the Musgrave Block moved. The timing compression across the 5 events is the detail that elevates this sequence from interesting to genuinely demanding of explanation. The Tonga event followed a period of elevated geomagnetic conditions by approximately 48 hours. The Japan event by a similar interval within the same disturbance window. The Vanuatu event occurred as a new disturbance interval was developing. The Maluku event followed renewed geomagnetic enhancement by roughly 24 to 48 hours. and the Uluru event followed the KP peak by 36 hours, the tightest temporal alignment in the entire sequence. This apparent compression of the lag time between geomagnetic disturbance and seismic response, from roughly 48 hours at the beginning of the sequence to 36 hours at the end, is a detail that researchers examining this data set have noted as structurally unusual. Whether it reflects a real physical process or is a pattern imposed by a small dataset onto noisy data is precisely the question that cannot yet be answered definitively. But it is not a detail that can be easily set aside. To understand the space weather side of this story properly, we need to go to the source, the Sun, not in the superficial sense of a hot glowing sphere 150 million kilometers away, but in the sense of the dynamic, magnetically complex, constantly erupting engine of space weather that drives the electromagnetic environment of the entire inner solar system, and, in ways that are still being actively investigated, potentially influences the geological behavior of the planet closest to it. The Sun is a star of ordinary size and composition by cosmic standards, a G-type main sequence star that has been fusing hydrogen into helium at its core for approximately 4.6 billion years and will continue to do so for approximately another 5 billion. But ordinary by cosmic standards is extraordinary by any human frame of reference. The Sun contains 99.86% of all the mass in the solar system. Its diameter is approximately 1.4 million kilometers, more than 100 times the diameter of Earth. Its surface temperature is approximately 5,500 degrees Celsius, and its corona, the outer atmosphere that extends millions of kilometers into space, reaches temperatures of 1 to 3 million degrees, a fact that remains one of the unresolved mysteries of solar physics. The coronal heating problem, why the corona is so much hotter than the surface it sits above, has defied complete explanation for decades and represents one of the most interesting open questions in solar science. What drives space weather is not the Sun's steady-state output of light and heat, but its magnetic field. The Sun's magnetic field is generated by the complex, turbulent motion of charged plasma in its interior, a process called the solar dynamo. Unlike Earth's relatively simple magnetic field, with a single north pole and a single south pole, the Sun's magnetic field is extraordinarily complex, with multiple polarities, twisted and tangled structures, and a geometry that changes continuously as the solar plasma rotates differentially, with the equatorial regions rotating faster than the polar regions, winding the magnetic field lines into ever tighter and more complex configurations over time. This differential rotation is the engine of solar magnetic activity. As field lines are wound tighter and tighter over successive solar rotations, they store increasing amounts of magnetic energy. When they become so tangled and stressed that they can no longer maintain their configuration, they erupt. The scale of the energy release depends on the complexity and intensity of the magnetic structure involved. A small eruption produces a minor solar flare. A major eruption of a particularly large and complex active region can produce the most energetic events in the solar system. X-class flares that briefly outshine the entire Sun in X-ray wavelengths, accompanied by massive coronal mass ejections that expel billions of tons of magnetized plasma into interplanetary space. The Sun's magnetic activity is not constant. It follows an approximately 11-year cycle, the solar cycle, during which the overall level of activity rises from a minimum to a maximum and back again. At solar minimum, the sun is relatively quiet. Few sunspots, few flares, few major CMEs. At solar maximum, the sun is highly active. Sunspot numbers peak, active regions multiply across the solar disk, and the frequency of significant space weather events increases substantially. The current solar cycle, Solar Cycle 25, which began in December 2019, has been more active than the consensus prediction from the Solar Prediction Panel assembled before its onset. Those forecasts anticipated a moderate cycle comparable to the relatively weak Solar Cycle 24. Instead, Solar Cycle 25 has been producing sunspot numbers and flare activity comparable to some of the more active cycles of the mid-20th century, and its maximum, which occurred in late 2024 and early 2025, was among the most active in several decades. This elevated solar activity level is the background context against which the March-April 2026 space weather events occurred. The Sun in early 2026 was not at its absolute maximum, but it was still in an active phase of the cycle, with a higher than baseline rate of coronal hole formation, CME production, and geomagnetic storm occurrence. Understanding the specific space weather drivers of the March-April window requires understanding two distinct mechanisms of solar wind enhancement. The first is the coronal mass ejection, a discrete eruption of magnetized plasma from the solar corona that propagates through the inner solar system as a coherent magnetized cloud. CMEs are produced by the sudden release of stored magnetic energy in active regions, complex sunspot groups where the magnetic field has been wound into unstable configurations by differential rotation and flux emergence. When a major active region erupts, the overlying magnetic field structure becomes unstable, reconnects in a catastrophic reconfiguration, and releases its stored energy in a fraction of a second. The radiation from this process is the solar flare, the electromagnetic component traveling at the speed of light. The physical expulsion of plasma is the CME, the particle component, traveling at speeds that can range from a few hundred to several thousand kilometers per second, depending on the energy of the eruption. A typical CME takes 1 to 3 days to travel from the Sun to Earth, and its arrival at Earth's magnetosphere, if it is directed at Earth and if it carries a southward-oriented magnetic field, drives geomagnetic storms. The second mechanism is the high-speed solar wind stream from a coronal hole. Coronal holes are persistent regions of open magnetic field on the Sun's surface, areas where the magnetic flux does not close back on itself, but opens into interplanetary space, creating a corridor through which solar wind can escape at much higher velocities than from the surrounding closed field regions. High-speed streams from coronal holes travel at 500 to 800 kilometers per second compared to the typical solar wind speed of 400 kilometers per second. And when they sweep past Earth, they compress the magnetosphere and drive geomagnetic disturbances that are typically less intense but more sustained than CME-driven storms. Because coronal holes rotate with the Sun, high-speed streams from persistent holes arrive at Earth approximately every 27 days, the Sun's synodic rotation period, creating a recurrent pattern of geomagnetic activity that space weather forecasters can anticipate with reasonable confidence. The March to April 2026 space weather sequence appears to have involved both of these mechanisms operating simultaneously and in overlapping fashion. A persistent coronal hole was producing recurrent high-speed stream arrivals on a roughly 27-day cadence throughout the early months of 2026. Superimposed on this baseline of elevated activity were one or more CMEs produced by active regions that were present on the solar disk during late March. The interaction of CME-driven disturbances with the preconditioned magnetosphere, already under pressure from high-speed stream activity, created conditions for sustained and compounding geomagnetic effects, the kind of overlapping, stacked driving that produces radiation belt enhancements lasting days to weeks rather than hours. By the time the G3 storm of April 3rd arrived, the magnetosphere had been in a state of elevated disturbance for more than 2 weeks. It had not recovered. It was not at baseline. It was a system that had been repeatedly compressed, energized, and agitated without being given sufficient storm, but a sustained, compounding, multi-driver period of geomagnetic disturbance during the equinox season, when coupling between the solar wind and Earth's magnetosphere is geometrically maximized during an active phase of solar cycle 25. In the history of space weather observation, this combination of factors is not unprecedented, but it is also not routine. It is the kind of period that space weather researchers recognize as a sustained high-activity interval, the kind that strains power grid infrastructure, degrades satellite operations, and, in the question that this documentary asks, may have consequences for the electromagnetic environment of the solid Earth below. When a geomagnetic storm arrives at Earth, what actually happens? Not in the abstract sense of the magnetosphere being disturbed, but in the concrete, physical, measurable sense of what changes in the near-Earth environment and what those changes propagate downward into. Because the pathway from a solar wind disturbance to a potential interaction with the solid Earth is a chain of physical processes, and each link in that chain needs to be understood clearly before the question of seismic influence can be evaluated rationally. The process begins at the magnetopause, the outer boundary of Earth's magnetic field, where the solar wind pressure and the magnetic pressure of Earth's field are in equilibrium. Under quiet solar wind conditions, the magnetopause sits at approximately 10 Earth radii on the sunward side, about 65,000 kilometers from Earth's center. When a strong solar wind gust, or CME, arrives, the increased dynamic pressure of the solar wind pushes the magnetopause inward, compressing it to as little as 6 or 7 Earth radii in extreme events. This compression is not gentle. It is accompanied by an impulsive pressure wave that propagates through the entire magnetospheric system, a sudden commencement of a geomagnetic storm that can be detected on ground-based magnetometers as a sharp, brief increase in the horizontal component of the magnetic field. This initial compression phase is followed, if the CME or solar wind carries a southward-oriented magnetic field, by the main phase of the storm, the period of sustained energy input through magnetic reconnection that drives the most intense geomagnetic disturbances. Magnetic reconnection at the dayside magnetopause is the key energy transfer mechanism. When the interplanetary magnetic field carried by the solar wind is oriented opposite to Earth's magnetic field at the magnetopause, when it points southward, anti-parallel to Earth's northward-pointing field lines, the two field systems can connect. Field lines from the solar wind and from Earth's magnetosphere meet at the boundary and snap together, reconfiguring into new topologies that allow solar wind plasma and energy to flow directly into the magnetosphere. The reconnected field lines are swept back by the solar wind flow, arching over the poles and into the magnetospheric tail, where they accumulate until a second reconnection process occurs in the tail, releasing stored energy and accelerating plasma earthward. This cycle of reconnection, energy loading, and release drives the ring current, a belt of energetic ions circling Earth in the inner magnetosphere, to intensify dramatically during the main phase of a storm. The ring current, when intensified, generates a magnetic field that partially opposes Earth's dipole field, causing the globally average decrease in the surface magnetic field that defines a geomagnetic storm in operational terms and is measured by the DST index. None of this is happening in isolation from the atmosphere and the ground below. The intensified ring current drives strong current systems in the ionosphere. The Birkeland currents, which flow along magnetic field lines from the magnetosphere into the ionosphere at high latitudes, and the auroral electrojet, a powerful horizontal current system flowing in the ionospheric E layer at altitudes of 100 to 150 kilometers. It is these ionospheric current systems that produce the aurora, the curtains and arcs of glowing light at high latitudes that are the most visible manifestation of geomagnetic storms for ground observers. But the auroral electrojets also generate rapidly time-varying magnetic fields at Earth's surface, variations that can reach tens to hundreds of nanoteslas per minute during intense storms. And it is these time-varying fields that drive geomagnetically induced currents in conductive structures on and below Earth's surface. Geomagnetically induced currents, GICs, flow in any extended conductive structure that is exposed to the time-varying magnetic field of a geomagnetic storm. Long-distance power transmission lines act as efficient antennas, collecting induced currents across their entire length and delivering them to transformers and substation equipment that was not designed to handle DC bias currents of the magnitude that GICs can produce. During the March 1989 Hydro-Quebec geomagnetic storm, a severe G5 event, the GICs induced in the Quebec power grid were strong enough to saturate the cores of high-voltage transformers, causing them to overheat and trip their protective relays within 90 seconds of storm onset, cascading into a total grid collapse that left 6 million people without power for up to 9 hours. In Sweden, during the same event, a transformer was permanently damaged. In South Africa, during the 2003 Halloween storms, 15 large power transformers were damaged, some permanently, requiring years to replace. These are not marginal effects. They are engineering failures caused directly by electromagnetic coupling between the space environment and conductive infrastructure on the ground. The Earth's crust is also a conductive structure, not a uniform one, and not as efficiently coupled as a purpose-built long-distance transmission line, but a conductive structure nonetheless, and one that extends to enormous depths, presenting a vastly larger cross-section for GIC induction than any man-made system. The GICs that flow in the crust during geomagnetic storms are real. They are measurable in some settings. They are part of the same physical phenomenon that damages power transformers, just operating in a different and far more complex medium. What happens when significant electric currents flow through the Earth's crust? In most of the crust, under most conditions, the answer is very little of mechanical consequence. The currents are weak, the rock is resistive, the effects are negligible. But the crust is not uniform. It contains fault zones, regions of fractured, fluid-saturated, often more electrically conductive rock embedded in the surrounding more resistive matrix. And in fault zones that are already mechanically stressed, the interaction of induced currents with the pore fluid system is the proposed mechanism by which the electromagnetic forcing might produce mechanical effects. The physics of this interaction involves electrokinetic phenomena, specifically the coupling between electrical current flow and fluid flow in porous media. When an electric current flows through a fluid-saturated porous rock, it drives the charged ions in the fluid along the current path. This ion movement creates pressure gradients, higher pressure where ions are accumulating, lower pressure where they are being depleted. In a fault zone, where the pore fluid pressure is already high due to the weight of the overlying rock column, a small additional increment of pore fluid pressure is not trivial. As discussed earlier, the effective normal stress on the fault, and hence its frictional resistance to slip, is reduced by any increase in pore fluid pressure. A fault zone that is already at 99% of its failure threshold may need only a fractional percent increase in pore fluid pressure to cross into failure. And the electrokinetic pressurization driven by GIC flow through the fault's pore fluid system, while small in absolute terms, could in principle provide that fractional increment. This is the mechanism. It is physically grounded. It is not invented. It is derived from first principles of electromagnetism and fluid mechanics. What it is not is proven in the context of natural fault systems at seismogenic depths. The laboratory measurements that establish the electrokinetic coupling coefficients for geological materials have been made. The theoretical models that translate those measurements to fault zone scales have been developed. What has not been done, what cannot currently be done with available data, is to directly measure the pore fluid pressure response in a natural fault zone to a geomagnetic storm event and correlate it with the timing of seismic activity. That measurement would require instrumentation at depths of 10 to 20 kilometers in an active fault zone, a technically formidable challenge that has not been achieved at the required resolution anywhere in the world. We return now to the Musgrave block, because it is the event that strains every framework we have discussed and demands the most careful treatment. The 4 Ring of Fire earthquakes, while temporally compressed and spatially broad, can be accommodated within existing models of interplate seismicity and potentially within the electromagnetic coupling framework, given the relatively favourable conditions for GIC interaction with warm, fluid-rich, tectonically active fault zones. The Musgrave block event cannot be so easily accommodated, and working through exactly why and what that difficulty tells us is where the most scientifically interesting territory of this entire investigation lies. The first challenge is electrical. As discussed in our examination of GIC physics, the efficiency of electromagnetic coupling between the space environment and fault zone mechanics depends critically on the electrical conductivity of the crustal pathway connecting them. Conductive pathways allow GICs to penetrate to depth. Resistive pathways attenuate them rapidly, limiting their reach and their potential to interact with deep fault systems. The Musgrave block is, by the most straightforward assessment of its geology, resistive. The dominant rock types, Archean and Proterozoic gneisses, granites, and high-grade metamorphic rocks, are among the least electrically conductive materials in the continental crust. They are cold, relatively dry, and composed primarily of silicate minerals with low intrinsic conductivity. On the basis of surface geology alone, one would predict that GICs penetrating the Musgrave block would be attenuated quickly and would not efficiently reach the depths of 10 to 15 kilometers where the April 4th earthquake occurred. But surface geology does not fully describe the electrical structure of the crust at depth. Magnetotelluric surveys, which use natural variations in Earth's electromagnetic field to probe crustal conductivity structure, have revealed that the continental crust is almost everywhere more electrically complex at depth than surface geology predicts. In particular, deep conductive zones, layers of significantly enhanced conductivity in the lower crust at depths of 20 to 40 kilometers, have been identified beneath cratonic regions globally, including parts of Australia. The origin of these deep conductive layers is debated. They may represent saline fluids trapped in porous or fractured lower crustal rocks, remnants of ancient tectonic events that introduced water-rich fluids into the deep crust and sealed them there under the confining pressure of the overlying rock column. They may represent graphite-bearing shear zones, ancient ductile deformation zones, where the metamorphic transformation of organic carbon-bearing sedimentary rocks produced seams of highly conductive graphite that persist to this day. They may represent zones of partial melting in the lower crust, where elevated temperatures have produced a small fraction of melt that dramatically increases local conductivity. Whatever their origin, these deep conductive zones create potential pathways for electromagnetic energy to penetrate to significant depths in the crust, even in settings where the shallow geology would predict resistive behavior. Whether such zones exist beneath the specific fault that ruptured on April 4th is not currently known. The magnetotelluric coverage of the Musgrave Block region is not sufficiently detailed to resolve conductivity structure at the resolution required to answer this question. That absence of data is itself a finding. It tells us that the assumption of electromagnetic decoupling in this region is based on incomplete knowledge rather than on definitive measurement. The second challenge is mechanical. The Musgrave Block is frequently described as stable, but as we discussed in the deep time section, this description can be deeply misleading if it is interpreted as synonymous with stress-free or mechanically inert. The Australian plate is moving. It is transmitting stress through its interior. The Musgrave Block contains ancient fault structures from the Petermann orogeny, structures that have been reactivated in recent geological history, as demonstrated by the 2016 Petermann earthquake and the 1988 Tennant Creek sequence. The absolute stress state in the deep crust of the Musgrave Block is not well constrained by direct measurement. We have surface GPS velocities that tell us about the broad pattern of plate motion. We have earthquake focal mechanisms that tell us about the orientation of stress at the time of individual ruptures. What we do not have is a high-resolution, depth-resolved model of the absolute stress magnitude on individual fault segments in the Musgrave Block, the kind of data that would tell us how close any given fault was to failure at any given time. The April 4th rupture itself demonstrates that at least one fault in the region was close enough to failure to rupture. What we cannot determine retroactively is the precise proximity to failure immediately before the event. Was this fault at 99% of its failure threshold, such that the merest whisper of additional perturbation could have triggered it? Or was it at 90%, requiring a more significant nudge? The answer to that question determines how much explanatory weight the electromagnetic coupling hypothesis needs to carry to account for the timing, and we simply cannot answer it with available data. The third challenge is the absence of precursory seismicity. In many fault systems, an earthquake of magnitude 5.5 is preceded by a period of elevated microseismicity. Small earthquakes, often too small to feel, but detectable by sensitive instruments, that reflect the progressive loading of the fault as it approaches failure. This foreshock activity, where it occurs, provides a signal that the fault is approaching rupture and allows seismologists to identify the fault system as one of elevated current interest. In cratonic regions, this foreshock activity is often absent. The stress invisibility problem discussed earlier means that the fault approaches failure without communicating its approach through detectable precursory signals. The April 4th event was not preceded by a detectable foreshock sequence in the available seismic monitoring data. Whether this reflects a genuine absence of precursory activity or simply inadequate monitoring density in the region is not clear. The seismic network coverage of Central Australia is sufficient to detect moderate earthquakes, but not the microseismicity at the level that might reveal precursory patterns. This ambiguity compounds the others. We cannot see the stress state. We cannot see the conductivity structure at depth. We cannot see the precursory loading history. We are working from the outside of a system whose, in various forms, for more than a century, and the history of how that question has been investigated, what answers have been proposed, why those answers have been challenged, and where the field stands today is a story that tells us as much about how science works in complex systems as it does about the specific relationship between the Sun and the Earth's interior. The earliest systematic investigation of a possible solar seismic connection dates to the late 19th and early 20th centuries, when the simultaneous development of global seismograph networks and systematic solar observation first made it possible to compare earthquake catalogues with records of solar activity. The motivating observation was straightforward. Solar activity follows an 11-year cycle, and some researchers noticed apparent periodicities in earthquake frequency that seemed to align with solar cycle timing. These early studies suffered from serious methodological limitations. The global seismic catalogues were incomplete and uneven in quality. The solar activity records were similarly incomplete before the advent of systematic daily sunspot observation, and the statistical methods available to researchers of that era were not sophisticated enough to distinguish between genuine correlations and the kind of spurious patterns that naturally emerge when noisy, cyclical datasets are compared. The conclusions were invariably mixed. Some researchers finding compelling evidence for a solar seismic connection, others finding no such evidence in the same data. The field developed a reputation for producing results that were difficult to replicate and impossible to definitively confirm or refute. The middle decades of the 20th century saw periodic revivals of interest in the question, usually triggered by periods of elevated solar activity coinciding with notable seismic events. The relationship between the 1957 to 1958 International Geophysical Year, a period of intense solar and geophysical observation that coincided with the maximum of solar cycle 19, one of the most active solar cycles in the instrumental record, and the seismic activity of that period attracted renewed attention. Soviet researchers in particular devoted significant effort to the question during this period, publishing analyses suggesting correlations between geomagnetic activity and earthquake frequency at various lag times. These studies were often methodologically more sophisticated than their earlier predecessors, but they continue to suffer from the fundamental challenge of all correlation research in complex systems: the inability to distinguish genuine causal relationships from coincidental associations in the absence of a physically specified mechanism. The turning point in the scientific quality of the discussion came in the 1990s and 2000s with the development of physically grounded mechanism proposals, the electromagnetic induction framework, the idea that geomagnetically induced crustal currents could interact with fault-zone fluid systems through electrokinetic processes to produce small but potentially significant perturbations in fault stability, provided for the first time a pathway that could be specified physically and investigated independently of the earthquake catalogue. Masashi Hayakawa and colleagues at the University of Electrocommunications in Japan developed theoretical models of ionosphere-lithosphere electromagnetic coupling. Oleg Molchanov and others in Russia investigated deep electromagnetic phenomena associated with earthquake preparation zones. Friedemann Freund at NASA Ames Research Center proposed a different mechanism, the generation of electrical charge carriers in stressed rock through the breaking of peroxy bonds in silicate minerals that could produce electromagnetic signals both before and potentially after earthquake preparation. These diverse research programs, operating from different theoretical frameworks and using different observational approaches, collectively established that the electromagnetic environment of the solid Earth is not isolated from the space weather environment above it, that coupling pathways exist and are physically real, even if their magnitude and their consequences for seismic behavior remain uncertain. The statistical side of the research also matured during this period. Researchers began applying more rigorous methods, superposed epoch analysis, Monte Carlo significance testing, careful control for background seismicity rates and seasonal effects, to the question of whether geomagnetic storms are followed by elevated seismicity rates at statistically significant levels. The results of these more careful analyses have been consistently more modest than the early enthusiastic reports, but they have not been uniformly negative. A 2002 study by Catarina da Silva and colleagues, examining earthquake catalogues from seismically active regions, found a statistically significant excess of earthquake occurrence in the days following geomagnetic storms compared to control periods, a result that survived several subsequent methodological challenges. A 2003 study by Oleg Sorokin and colleagues found similar results using different catalogue and analysis approaches. Other studies, including several specifically designed to test these earlier positive results, found no statistically significant effect. The literature is genuinely divided, not in the sense of fringe versus mainstream. Both sides of the debate are represented by credentialed researchers publishing in peer-reviewed journals, but in the sense of genuinely contested science, where the question has not been resolved and where reasonable scientists examining the same evidence reach different conclusions. This is uncomfortable for anyone seeking a clean answer, but it is an honest description of where the field actually stands. The question is not settled. It is not answered in the negative with the confidence that skeptics sometimes express, but it is also not answered in the positive with the confidence that enthusiasts sometimes claim. It sits in genuine scientific uncertainty, the kind of uncertainty that only more and better data can resolve. What would the research community need to see to shift the balance of evidence meaningfully in one direction or the other? On the positive side, a demonstration that the timing correlation between geomagnetic storms and seismic events persists across large, globally complete earthquake catalogues at statistically significant levels after rigorous control for all known confounding factors, combined with direct physical evidence of the proposed coupling mechanism operating in real fault zones at seismogenic depths. That second requirement is the harder one. It demands borehole instrumentation at 10 to 20 kilometer depth in active fault zones, continuously monitoring pore fluid pressure, electrical conductivity, and microseismicity, simultaneously with space weather conditions. Such installations exist in limited form. The San Andreas Fault Observatory at Depth, or SAFOD, and the Nankai Trough Seismogenic Zone experiment in Japan represent examples of deep borehole fault zone observatories. but none have been specifically designed to monitor electromagnetic coupling from space weather events, and none are located in the intraplate settings that the April 2026 sequence suggests are most in need of investigation. On the negative side, a comprehensive demonstration that the apparent correlations in the existing literature can be fully accounted for by known tectonic mechanisms, aftershock dynamics, and statistical artifacts, with no residual signal requiring an external electromagnetic driver. That demonstration has also not been definitively made. The negative case has been argued effectively for individual datasets and individual studies, but the accumulation of positive findings across diverse research groups using diverse methods is not trivially dismissed. We have now travelled a long distance from the moment on the morning of April 4th, when the ground moved 77 kilometres from Uluru, and guests in a hotel felt the Earth announce itself in the language it has been speaking for 4.5 billion years. We have gone into the deep structure of ancient rock, into the physics of fault mechanics, into the electromagnetic dynamics of the Sun-Earth system, into the history of a scientific debate that has persisted for more than a century without resolution. It is time to bring it together, not with false certainty, but with the precision that the evidence actually supports. Here is what we can say with confidence. The 14-day seismic sequence from March 24th to April 4th, 2026 is statistically unusual. 5 major earthquakes, 4 along the Western Pacific Ring of Fire, and 1 in the interior of the Australian craton, occurring within a compressed 2-week window, all during a sustained period of elevated geomagnetic activity culminating in the strongest geomagnetic storm of the year, is a clustering of events that deserves more than a dismissal as ordinary background seismicity. The probability of such a sequence arising by chance from the random fluctuations of a globally active but otherwise normal seismic system is not zero, but it is low enough to justify serious analytical attention. Here is what we cannot say with confidence. We cannot say that the geomagnetic storms caused the earthquakes. We cannot say that the sun triggered the Uluru event. We cannot say that there is a proven physical mechanism linking space weather to seismic timing in either the Ring of Fire settings or the cratonic setting. What the evidence presents is a correlation, a temporal alignment between space weather events and seismic events that is more tightly structured than a purely coincidental distribution would predict. Correlation, as the overused but still essential cliché reminds us, is not causation, but it is also not nothing. Correlations in complex natural systems are signals. They are the first language in which genuine causal relationships announce their existence, long before the mechanisms that produce them are understood. The history of science is full of correlations that preceded mechanisms. The correlation between smoking and lung cancer was documented decades before the precise molecular mechanisms of carcinogenesis were understood. The correlation between hand hygiene and reduced mortality in hospitals was established by Ignaz Semmelweis in the 1840s, 2 decades before germ theory provided the mechanism. Correlation is not proof, but sustained, reproducible, physically coherent correlation is what motivates the search for mechanisms. And the solar seismic correlation, whatever its ultimate status, has been sustained across multiple decades of observation and multiple research groups, examining it from different methodological approaches. The April 2026 sequence adds one genuinely new element to the evidentiary landscape, the presence of a cratonic interior event in the temporal cluster. Previous correlation studies have primarily examined seismicity in tectonically active regions, where the electromagnetic coupling mechanism has its strongest theoretical basis. The inclusion of a cratonic event in a sequence otherwise dominated by ring of fire events expands the potential domain of the coupling, if it exists, to geological settings that standard models would classify as insensitive to external electromagnetic perturbations. That expansion either reveals a real physical effect operating more broadly than previously suspected, or it reveals a pattern that is the result of statistical coincidence operating across a sequence that is large enough to include a randomly timed intraplate event. The honest assessment is that 5 events across 14 days is not a sufficient dataset to distinguish between these interpretations. What this sequence does is narrow the interpretive space and sharpen the question. It defines more precisely the boundary conditions that any complete theory of Earth-space coupling would need to satisfy. And it identifies the Australian cratonic interior as a geological setting where improved observational infrastructure could produce data genuinely capable of advancing the scientific debate. More seismometers, better coverage of microseismicity, magnetotelluric surveys to map deep crustal conductivity structure, borehole stress measurements. These are not exotic or speculative research tools. They are standard geophysical methods that have simply not been deployed in intraplate regions at the density that the scientific questions now demand. The broader significance of this sequence extends beyond the specific question of solar seismic coupling. It is a reminder that the Earth system is not a collection of independent processes operating in isolation from each other and from the space environment that surrounds the planet. The solid Earth, the fluid Earth, the atmosphere, the ionosphere, the magnetosphere, and the solar wind are coupled systems, linked by flows of energy, momentum, and electromagnetic influence that cross the boundaries between them in ways that are still being mapped. The history of Earth science has been a progressive recognition of these couplings, from the discovery of the global atmospheric circulation to the recognition of ocean-atmosphere coupling in phenomena like El Niño, to the understanding of how volcanic eruptions can alter global climate, to the documentation of how tidal forces can influence the timing of volcanic activity. Each of these couplings seemed improbable or speculative before it was established. Each required a period of anomalous observations, contested correlation studies, proposed mechanisms, and finally definitive observational proof before it entered the accepted scientific canon. The question of Earth-space electromagnetic coupling in the context of seismicity is at an earlier stage of this progression. It is not yet established, but it is not as speculative as it was a decade ago. And the sequence of events in March and April 2026 moves it, by a small but measurable amount, in the direction of demanding a definitive answer. There is a perspective available to us that is unique to the kind of deep geological contemplation that this documentary has attempted to provide. A perspective that the immediate news cycle, with its pressure toward resolution and conclusion, almost never reaches. It is the perspective of deep time itself, of what the Earth looks like when you step back far enough to see not years or decades, but millions and billions of years. From that perspective, the earthquake near Uluru on April 4th, 2026, is not an anomaly. It is a single heartbeat in a 4.5 billion year rhythm. The Musgrave block has moved before. It will move again. The ancient fault that ruptured on April 4th has a history of deformation stretching back hundreds of millions of years. A history of repeated loading, rupture, healing, and reloading that will continue long after every human who was alive on April 4th, 2026 is gone. The Sun has been generating magnetic storms for 4.5 billion years. It will continue generating them for another 5 billion. The Van Allen belts have been swelling and contracting in response to solar forcing since Earth first developed a significant magnetic field, approximately 3.5 billion years ago. These are ancient, ongoing processes. What is new is not the processes themselves, but our ability to observe them simultaneously, to correlate them across systems, to ask whether the apparent relationships we see in our few decades of instrumental observation reflect real physical couplings or coincidental alignments in a system too complex for us to fully see. The honest answer is that we do not yet know. But the question is real. The physical mechanisms are plausible. The observations are reproducible enough to resist dismissal. And the scientific tools required to resolve the question definitively, if deployed in the right places with the right patience, exist. What happened near Uluru on April 4th will not be the last time this question presents itself. The Sun will continue to storm. The Australian craton will continue to accumulate stress in its ancient, silent way. The next time an intraplate earthquake coincides with a geomagnetic storm, it will add another data point to a slowly growing body of evidence that is edging, with geological patience, toward an answer that our instruments are only now becoming capable of providing. The rock beneath the Australian outback has returned to silence. The Musgrave block rests once again in the patient stillness of 3 billion-year-old stone. The solar wind continues its constant flow past a spinning, magnetically shielded, seismically active planet. And somewhere in the deep crust, along ancient fault zones that formed before the first complex life evolved on Earth, stress accumulates in ways we cannot yet see, waiting for a moment that our models cannot yet predict, in a system whose full complexity we are only beginning to understand. The Earth keeps records. In rock layers and fault scarps, and the deep electrical structure of ancient continental cores, we are still learning to read them, and what the earthquake near Uluru tells us, quietly, in the language of seismic waves and ancient stone, is that there are still pages in those records that we have not yet turned. This has been Geovast. The Earth has no shortage of stories. We will keep reading them.